All right, folks. So today we're going to take a look at putting some of our skills together. We're going to consider the skills we learned in section 3.3. We'll try and factor our functions from standard form to factored form so that we can sketch a function not only if it's in factored form, but that we can sketch functions that are given to us in standard form as well. Now, we already do know how to sketch a function if it looks like this, if it's in factored form. Nice and easy. If I'm taking a look at this, I can analyze. First, I can take a look at the degree of my polynomial here. I have a 2, I have a 3, I have a hidden 1 there. I can add up those degrees. The degree of this polynomial equals 6. Okay, and then I can take a look even further. My a value here is -1. -1 is less than 0. So my end behaviors as x approaches positive or negative infinity, y will approach negative infinity. So my end behaviors are in these general directions down here. Now, once I have my end behaviors, I can look even further. I can take a look at the roots of my function here. I see a double root, again, because of the exponent I'm working with here. This is a double root, and it's at x equals -1. I have a triple root here at x equals +1, and a single root, again from the exponent on my brackets, a single root at x equals 2. So I can start to draw those in here. I have a double root at x equals -1. Put that right here. A double root. I have a single root at x equals +2. And let's even spread this out. We'll change our scale a little bit here at +2. And a triple root at x equals +1. Fantastic. And number 3, I can take a look and I can find, and you should be pretty comfortable doing this, I can find my y-intercept by setting x equal to 0. So I'm working with negative 0 plus 1 squared, 0 minus 1 cubed, 0 minus 2. I can multiply those together. That is -1 squared times -1 cubed times -2. And I'm working with here, let me see, I should end up with -2. Okay, so there is my y-intercept. Again, at x equals -1, it's a double root I'm working with here. At x equals +1, it's a triple root. So my function behaves like a cubic function. And at x equals 2, it's a single root. So I can put all of these together. I should end up with, and you know what, I'll give it another color for the parts that I'm just kind of guessing here, that I'm piecing together, where I have a little bit more flexibility. Something like this. So my polynomial could look like this. Again, we know how to graph this. If you're a little confused here, you can go back to the video from 3.3. Now again, though, if we're graphing this, the only reason we're able to do so, we're able to find these roots, is because this function is in factored form. So we need to be able to find the factored form for a function if we want to graph them. Sometimes we're given them in standard form. We'll work with that here. We'll kind of explore a little bit and see where it goes. This one, we're not even defining it as a function yet, but we're going to divide our numerator by our denominator, our dividend by our divisor, using our synthetic division. You should pretty much be a master of this by now, so I'm just going to do it really quickly here. We'll see if I can do it while I chat without making any mistakes. Now, when we're doing this, make sure you're taking care. You're working with the root of your denominator, the root of your divisor. There's your k value. I'm sure you are very careful here. And you know what? It looks like I did make a mistake, so bear with me here. No mistakes, I just wasn't expecting it. Nice and easy, -3 plus 9, I'm working with a +6. So that means that if I were to give my quotient and remainder, then my quotient here would be x squared plus 2x minus 1 plus a remainder of 6. Okay, now, again, if I'm to write this with a multiplication statement, a concluding statement here, I need my dividend, that's x cubed minus x squared minus 7x plus 9 equals my divisor, which is x minus 3, times my quotient, that is x squared plus 2x minus 1 plus 6. Nice and easy. Now we want to evaluate this dividend at x equals 3. And I'll give you a moment to try that. Just put it into your calculator if you need to. That is, we're working with here 3 cubed minus 3 squared minus 7 times 3 plus 9. Even further, that is 27 minus 9 minus 21 plus 9. And that equals 6. What do we notice here? Well, we might notice that my remainder that we calculated over on this side, and I know we only went through one example here. This pattern will hold true. The remainder that I calculate up there will be the value of f if I evaluate f at the root of my divisor. Right? So if my divisor here is x minus 3, the root of my divisor is x equals 3. If I evaluate my function, my numerator, my dividend, at x equals 3, at x equals the root of my divisor, then I will find the remainder that I would find after dividing it. Now, why is this important? Well, that means that we can determine our remainder without going through any form of division, whether it's synthetic division or long division. Right? So if we evaluate f at x equals a, then if I were to divide f at x by x minus a, I would find the remainder f at a. That will also follow true if my function has a divisor that is still a linear divisor, but a linear divisor, if I'm taking the root of this linear divisor, my root will obviously be a over b. And if that's the case, the remainder is f at a over b. Now we'll try this out. If you're still a little bit confused, we'll try this out a little bit here. Okay, so I want you to use the remainder theorem to determine the remainder when this function is divided by this. Well, you might be tempted to throw this into synthetic division. Right, we can try that out right here, synthetic division. The root of my divisor is -2. My coefficients are 2, -4, 3, and -6. I can bring my 2 down. That's 2, -4, -8, 16, 19, -38, and let me see here, -44. Right, so this tells me that my remainder is -44. Well, instead of doing that, if we use our remainder theorem that we just found, we can simply evaluate our function. Whoops, I'm not sure how I even accidentally did that. We can evaluate our function at, I apologize, folks, allow me to fix what's going on. We can evaluate our function at the root of this divisor. The root is where x equals -2, and that is 2 times -2 cubed minus 4 times -2 squared plus 3 times -2 minus 6. Nice and easy. That's 2 times -2 cubed. Okay, so I'm working with -16. If you need to do this in a few more steps, that's absolutely fine. With the intention of keeping this video a little bit shorter than it could be, I'm just going to try and go at a pretty good pace here. -16 minus 6 minus 6, and I'm working here with -16 minus 16. That's -32. Minus 12, which equals -44. Okay, so I could have chosen either strategy In particular, if you have a calculator, this is nice and easy, but we're not going to have calculators on our assessment during this chapter. But either way, you still should find it a little bit easier, in particular with really simple divisors. You might find it a little bit easier to go through just evaluating our function at a certain point. Now, I want you to try it out right here. Find the root of 2x minus 1. Try to find the the remainder that would happen if we divide this dividend by the divisor. That final answer will be posted on the classroom afterwards. All right, now the remainder theorem tells us that f at a is the remainder when f at x is divided by x minus a. Now, what would that tell us if f at a equals 0? Well, if f at a equals 0, then the remainder equals 0. Now, if the remainder equals 0, then x minus a is a factor, which you may have remembered from the end of the lesson from 3.5. X minus a is a factor of the dividend. Okay, well, how can that help us? Oh, it can help us hugely. That can be the beginning to helping us find some factors. If we find a factor, we know how to divide them out. All of a sudden, we can put it together and we can start to fully factor longer polynomials. This gives us our factor theorem. Okay, now you should be pretty darn familiar with the name after you've worked through this lesson. With the name, this is a factor theorem. If I ask you on an assessment, what is the factor theorem, you should be able to tell me. If I ask you on an assessment, what is the remainder theorem, you should be able to tell me. Okay, you're at that point in your math careers where you should be able to handle stuff like that. Now, again, if you're not comfortable with it right now, that makes sense. You've only just learned what it is. But they are pretty straightforward theorems. Now, this factor theorem, if x minus a is a factor, x minus a is a factor of f at x if and only if. That's what the IFF stands for, if and only if. You may have seen that before, you may not have. If and only if f at a equals 0. And what that means is, if f at a equals 0, x minus a is a factor. If f at a does not equal 0, x minus a is not a factor. That's what the if and only if tells us. Okay, same thing if we have a root that has an a value, that has a leading coefficient not equal to 1. So if it equals b, say, then bx minus a will be a factor of f at x if and only if f at a over b equals 0, as in if f at the root of this factor equals 0. Now this makes sense. If we think about the sketch that we did at the beginning of this function, we took these roots and we said, okay, well, if I evaluate my function at the root of these factors, so say at x equals -1, then my function should equal 0. Right? If I evaluate my function at x equals +1, my function, my y value, should equal 0. That's all we're working with here. We'll keep right on going down here, and we'll try and use our factor theorem to factor some polynomials. Okay, so we'll try and factor this here. Now, when we start off, we're trying to guess and check. If we consider, and you know what, I think I have a better example down below. I do not. That's okay. If I'm looking at a simpler problem, let's say a quadratic. We all know how to factor some quadratics. If I'm working with x squared minus 6x plus 5. Then where I start, if I'm trying to factor this, then I start and I take a look at this 5. I'm not just guessing and checking random values. I take this 5 and I try and find factors of this 5 that will work with my middling term, right? In this case, -1, -5 is what would work for me if I'm trying to factor this. And then factored, it looks like x minus 1, x minus 5. Right? So what I'm working with are factors of my constant term. That's going to be the same starting point that we take when we're working with functions that have a degree greater than 2. So like this is a cubic function. It has a degree 3. We take our constant term. Our constant term is -12. And we want to use the factors of -12. So our possible roots are plus or minus, and really I can break it down. I can say, okay, -12, my factor is 1, negative 12, 2, negative 6, 3, negative 4, and then all of those negative versions. So negative 1, 12, negative 2, 6, negative 3, 4. So if I list all of those numbers, my possible roots are plus or minus 1, 2, 3, 4, 6, and 12. And you might say, Mr. Pasotka, that seems like an awful lot of work to check to see if every single one of these values is a factor of this polynomial. Well, you're right, it would be, but once we find just one factor, then all of a sudden it makes our lives much easier when we're trying to factor the rest, because it simplifies the problem. And you'll see what I mean here in a moment. Let's try positive 1 first. Okay, so we try to evaluate f at 1. That is, we're working with 1 cubed plus 2 times 1 squared minus 11 times 1 minus 12. Okay, well that is 1 plus 2 minus 11 minus 12. Okay, so f, I don't really care what this equals. All I care is if it equals 0. I can see a minus 11 minus 12 towards the end of that. That will not equal 0. So f at, well really, so x minus 1 is not a factor. Okay, great. Let's try one more. And really I should have, if I'd planned it out a little bit more, I would have left myself some more space. So let's try that out right here. Let's try now where x equals negative 1. Okay, so f at negative 1 equals negative 1 cubed plus 2 times negative 1 squared minus 11 times negative 1 minus 12. Okay, so I'm working right here. That is negative 1 cubed, that equals negative 1. 2 times negative 1 squared, that equals a positive 2. Minus 11 times negative 1, so plus 11 minus 12. And I can see right here, if I put that, and again, we're not using calculators, but if I put that into my mind, I add these up. Negative 1 plus 2 plus 11 minus 12. This equals 0. That tells me that x plus 1 is a factor. Okay, that's great. Now that I found 1, I can stop searching. Okay, now that I found 1, I can use my synthetic division to factor this x plus 1 term, this x plus 1 divisor, out of my dividend. So I can work right here. So let's work f at x divided by x plus 1. And I'll put that into my synthetic division here. My coefficients, 1, 2, negative 11, negative 12. My root of my divisor is x equals negative 1. And you'll notice that's the same value that I substituted into my function. Right, here I am. I'm dividing 1, negative 1. Again, you should be pretty much a master of this by now. If you're not, just a little more practice will help you. Negative 1, negative 12, positive 12, 0. And since I found this equals 0, that's good. That verifies for me. That confirms that I performed appropriate arithmetic over here to try and determine if it is a factor. Great, so it is a factor. Now I can put together my multiplication equation statement, my concluding statement here, where I'm working with my dividend x cubed plus 2x squared minus 11x minus 12 equals my quotient, which is x squared plus x minus 12, times my divisor, which is x plus 1. All of a sudden, I can see a problem here. If I'm trying to fully factor this polynomial, I can finish this off. I can finish the job with my grade 10 factoring skills. This is a simple trinomial. So I can fully factor it the rest of the way. That is x plus 4, x minus 3 times, and I cannot forget to bring down this factor that I already found, times x plus 1. And you notice here right off the start, I listed all of these possible roots. I tried them out. I listed them off so I could see some to try out. I only needed to try 2 of these until I found one factor. Once I found a factor, I was off to the races, and I was able to work forward and try and find more factors. Okay, I was not required to, and really I should have some brackets around these because it's plus or minus every single possible factor in here. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. In total there, I have 12 different factors, 12 different roots I could have checked, and all I needed to check was 2 of them because I was creative with what I did once I found a factor. Okay, so you should be able to try that out a little bit further. I'm going to, how's our time? We're doing okay. We'll try this one together here. We'll just think about it as we work forward in here. We're working with a little bit of a more advanced problem because of the coefficients we're working with here. So I encourage you, first take a look. Okay, we see our constant term. This one has very simple factors, right? The factors of positive 2 are plus or minus, and I'll pause here for you to try it on your own, plus or minus 1, plus or minus 2. That's it. So there are only 4 possible factors. I encourage you, try them all out. See if you can find one factor here. Evaluate f at 1, evaluate f at 2, evaluate f at negative 1, evaluate f at negative 2, until you find one possible factor. Right here, I'll say pause the video, try that out on your own, and you should find that none of these are factors. Okay, well, does that mean that this is an unfactorable polynomial? We'll see. We'll come back to it. Maybe there's a little more to it than we have considered so far. Let's consider, we'll push on forward a little bit here. Let's consider this polynomial, which is of the form you have worked with in grade 10 before, and we'll try and factor this. You should be able to factor this. If you're not able to, you need to practice factoring complex trinomials, whichever strategy you prefer to use. I am going to use decomposition here because it's one of the more popular strategies for factoring complex trinomials, but I won't care which strategy you use when you're working through something like this. So working with my decomposition, I take my A term and my C term, that's 12 and negative 10, I multiply them together, so negative 120. And then I try and find 2 values, 2 factors of negative 120, a factor pair of negative 120, that adds up to negative 7. Okay, so I'm multiplying to negative 120. I'm adding up to negative 7. And through a little bit of guess and check, a little bit of exploration here, we should be able to see that we're working with the factor pair negative 15 and positive 8. Okay, these add up to negative 7. So then I'm taking this negative 7, and really I should not be taking the time to minus 15x to explain decomposition in this course, but that's where I'm going in this video, so that's okay. Minus 10. And then I'm factoring out, it's like I'm grouping my first 2 terms, my last 2 terms. I'm factoring out the common factor, so in this case that is 3x, working with 4x minus 5, plus, and then just a 2, and leaving me with 4x minus 5 again. Then I'm common factoring my 4x minus 5 out, 4x minus 5, 3x plus 2. Okay, so I factored it. My roots here that I'm looking at, and let's write off in the other direction. I apologize for not leaving much space here. My roots are at x equals 5 over 4. Or x equals negative 2 over 3. All right, so if I consider where I began here to where I ended with my roots, I need to try and find a pattern, because clearly my roots did not only come from this final term, this negative 10, right? 5 over 4, negative 2 over 3, those are not factors of negative 10. So we need to ask ourselves, okay, what kind of work did we use to get here? Well, when I decomposed my function, I used negative 120. Well, I found negative 120 from my A term and my C term, from my leading coefficient and my constant term. So that's going to be where I'm working. You may notice over here, let's color code this a tiny bit more. From my constant term, you can see I found my numerators, right? 5, negative 2, that's a factor pair. Those are factors of negative 10. My denominators are factors, that is over 4 and over 3. My denominators are a factor pair of my leading coefficient, right? So it's a combination of the two that I need to consider when I'm working with these terms. So when determining possible rational zeros of a polynomial, rational, meaning we can state them in a fraction, we have to consider coefficients of both the first and the last terms. Okay, so then I can come back up here. I can return to example 4, and I'm working. Initially, I only considered factors of my constant term. Now I need to consider in my denominator factors of my leading coefficient. So I'm working here 1, and you know what? I'll color code this as well. 1 and 2, like I said, plus or minus 1 or 2 are in my numerator. But then for my leading coefficient, I'm working with factors of 18. Well, factors of 18, 1, 2, 3, 4 is not, 5 is not, 6 is, and 18. Right? Where all of a sudden I have plenty of options here. I only need one option that works. Right? Once I have one option that works, I can use that to work forward. Let me see here. Right, so I have listed this off. The possible rational zeros of the function are factors of the constant divided by factors of the leading coefficient. Now, when we're choosing to guess and check, to try and pick our factors, we want to work with the simplest values we can at the start to try and determine if a certain value is a factor, is a root of a factor of my polynomial. Okay, now we are going pretty quickly through here. If you're stumbling through it, that's okay. I encourage you, keep watching, so at least you have a little bit of an echo of the concepts that we're working with here. But either way, the possible factors that I'm working with, this is a bit of a concise way of writing. If I list them all out, then it's plus or minus 1 over 1, 2 over 1, 1 over 2, 2 over 2, which is equal to 1 over 1, so there's no need to write that one there. 1 over 3, 1 over 6, 1 over 18, 2 over 3, 2 over 6, well, that's equal to 1 over 3, so there's no need to write that one down. 2 over 18, that's equal to 1 over 6, there's no need to write that one down. So here are my possible factors. We want to try and choose the ones that are going to be simplest for us to evaluate. So I'm glad we already checked f at 1, f at 2, f at negative 1, and f at negative 2, because those would be the simplest ones to work with. Next, we work down the line, right? So 1 over 2, that's a little bit simpler. If I'm working with 1 over 2 cubed, I can figure that out. That's 1 over 8. Whereas if I'm working with 1 over 18 cubed, that's a much tougher calculation to do. It's not impossible by any means, and you should be able to handle that at this grade level. But this just involves a few more steps in evaluating what is 1 over 18 cubed. So let's work with the simple ones first. So we would try here, we would try and find f, we would try and evaluate f at 1 over 2, and f, maybe if that does not work, f at negative 1 over 2. Try them out, evaluate, see what you find. I'll pause here for a moment. Good, and we should be able to see that f at 1 over 2 equals 0. That's great. That is all we need. We just need to find one factor. If f at 1 over 2 equals 0, then that tells me the factor I'm working with, 2x minus 1, is a factor. And if 2x minus 1 is a factor, then I can work with this function. It is 18x cubed minus 15x. I know I'm kind of working sideways. Maybe I'll adjust this note so that you have a little bit more space there. I'm working with 18x cubed minus 15x squared minus x plus 2. I'm dividing this by the factor I just found, that is 2x minus 1. And you should be able to handle this with our synthetic division. I'm working with, okay, so the root of my factor, sorry, the root of my divisor here, or yeah, the root of my factor. I'm working with a 1 over 2 there. 18, negative 15, negative 1, and 2. Nice and easy. I bring down the 18. I multiply 18 times 1 over 2. That is 9. Negative 15 plus 9. I'm working with negative 6. Negative 6 times 1 over 2. That's negative 3. Working with negative 4. Negative 4 times 1 over 2. I'm working with negative 2. Good. I find the 0 here at the end. I'm confirming that it is a factor, and that means that my dividend, which is 18x cubed minus 15x squared minus x plus 2, equals my divisor, which is 2x minus 1, times my quotient, which in this case is 18x squared minus 6x minus 4. And all of a sudden, if I'm looking to factor this any further, I can again use my grade 10 math skills to do so. I encourage you to do that on your own. Pause the video right here as you work through that. Again, if you can't do that, folks, you are going to struggle in this chapter. You need to be able to factor complex, simple trinomials, perfect squares, difference of squares. You need to be able to see these patterns so that you can follow through with factoring at a grade 10 level. 2x minus 1, 3x minus 2, and 3x plus 1 is what we're working with right here. Okay, folks, if you're really struggling with grade 10 factoring skills, I have other videos on this channel that can help you out there from when I taught those courses in the past. Now, let me see here. Oops, there was actually a little more space for us to handle it down here, so I will leave the note as is. This is the same example that was copied from up above. And lastly, folks, I'll give you a bit of a challenge problem here. Okay, so if x plus 2 is a factor of this polynomial right here, x cubed plus 2x squared plus kx plus 6. You can see where this question's going. We need to try and find the value of k. Now, right away, folks, I'll encourage you, if this is your first time watching this video, if this is your first time seeing any of these concepts, stop here. Go back, practice the problems from the textbook that work with factoring simpler polynomials. And then when you're feeling more comfortable with those skills, then come back here and try it out. Okay, because if you're just following through with me going through the solution here, it's not going to be very meaningful unless you do have those background skills. Okay, I will go through this solution because I think there are good things that we can learn right here. Now, I'll give you a bit of a hint, folks. For any question you work with in this course, in other courses, for any question that asks you to determine the value of k, right? I'm sure many of you see problems and all of a sudden, as soon as you see a k involved, you think, oh no, this is not going to be fun, right? Because they test, they assess, they require a higher understanding of what you're doing. But really, what they mean, if you're trying to find the value of k, the first thing you need to ask yourself is the piece of information they gave me. What does that mean? Or what does that imply? Or what can that tell me? Right? That's all we need to do. Well, if x plus 2 is a factor of this entire polynomial, then that means f at negative 2, I'll pause here for you to try and work it out, f at negative 2 equals 0. Okay, if f at negative 2 equals 0, that should be able to help us, right? That means 0 equals x cubed plus 2x, 0 equals, let's line it up a little bit better. 0 equals negative 2 cubed plus 2 times negative 2 squared plus k times negative 2 plus 6. And you should then be able to isolate for k, because remember, k is what you're trying to find. So I'm hoping this, going through this solution with you, and I'm going to stop there. You can finish solving it on your own, but I'm hoping you can gain a little bit more skill at solving problems if you're trying to find the value of k. Math teachers love to give you that problem. All they're asking is, what does the first part mean, and can you use that information to find what k must equal? All right, so at this point, you should be able to handle it. I'm sorry for the long video. Again, I know some of the classes enjoy the long video. They appreciate it to get more examples. Other classes are a little bit intimidated by it, but I'm hoping it's useful for you. And this is the end of our third chapter. You should be feeling pretty good about your skills with polynomials at this point, or at least after you practice the practice problems here.